Good morning, everyone. So today, my name is Julian Bobe, coming from INRAE in France, in Rennes. I will be talking about microRNA annotation today. So as you, I'm sure, know, microRNAs are a class of small, non-coding RNAs of very short, 22 nucleotides, and they actually act on mRNA levels. They regulate mRNA levels through deadenylation and translation repression that will ultimately lead to mRNA decay. So that's how they work. And they are actually transcribed from genes that are processed into hairpins and then into short mature microRNA that will actually load onto the Argonaute complex to silence genes at the mRNA level. So we have several problems with microRNAs. One is it's difficult to annotate because they are short, and they are seed sequence that is actually recognizing the motif on the UTR of the mRNA can be highly conserved among mRNA families, and that's especially problematic in and not so much in mammals, for instance, but in teleost fish. Due to the additional rounds of full genome duplication, especially in all teleosts for starters, but then also in salmonids and carps. And we've been facing over the year many difficulties that are an over-prediction of the number of microRNAs by several tools, and the difficulty in providing an accurate annotation due to those duplications. There's also one other problem which I will not address today, is the difficulty is identifying their biological targets, and that's another story, and that's even much more complicated, but not today. Okay, so the approach that we've used is to pretty much, because the gene repertoire of microRNAs is much smaller than for protein coding genes, so the approach that we've used is to track all the genes, the microRNA genes, in teleost from before teleost genome duplication. So using like Holocene species like GAR or bofin, and to pretty much track all the genes, the gene repertoire in different species. So you see that we end up with approximately 300 microRNA genes in teleost, non-salmonid teleost. So the idea was to do that manually based on the expression, on the reads that we know, and then manually annotate that because again there's a limited number of genes, so we can do it manually, semi-manually. So this is included in a database that is called Fish microRNA, and in which we provide annotation, we provide expression data, like for instance here the expression of my favorite microRNA called miR202, which is a gonad-specific microRNA. And right now we have like up to 12 species in fish microRNA, and more are coming. And you can do BLAST, and you can find the link to the genomes, the link to ZFIN. And that's what we use to make the data available to everyone. So that's what we did before, and in the AQUA FAANG project, we developed, sorry for the small a, we developed a new pipeline to automatically annotate the microRNA genes based on synteny. So the idea is that we start from putative hairpins, and we try to get synteny support to automatically or almost automatically annotate microRNA genes. So first step is to identify putative hairpins from the prost, from the reads, the small reads that we have. So either we have a putative hairpin with two mature forms, flanking region of, and we had a flanking region on both sides, or we have only one form, and then we have to extrapolate based on the position of the mature. So it's either one. And we do some filtering with at least one mature with a sufficient coverage, and we need at least one mature that has been annotated before, even though if it's an imperfect match. And we remove overlapping hairpins, and with a preference for sequences that have 2 matures, of course, and the highest coverage. So, okay, this is our new genome with a putative hairpin, and we go for 15 coding genes downstream and upstream of the hairpin, and then we look for their orthologs in fish using the Genomicus website, in which we have many species, and that's also totally available to everyone. And then we are going to try to blast the hairpin to the other genomes and find putative homolog hairpins, putative orthologs. And then we will find neighboring genes and see if they're orthologs to the one that are neighboring genes of the putative hairpin. It's super simple, really, nothing tricky. And then, based on that, we decide to keep the best homolog with at least two conserved genes on one side. That's the criterion that we use so far. Okay, and this is the result we got for rainbow trout, and you can so here are all the species that we have in the pipeline, and you can see that that's the number of annotated microRNAs. Okay, so the way you have to read that, it's for rainbow trout microRNAs. We have 300 microRNAs that can be annotated based on this species. Okay, and you see that the most contributing species is Umbra pygmae, which is the sister group of salmonids just before duplication. So it actually totally makes sense. And you see that most microRNAs are supported, annotation are supported with at least 2 species and some with even more species. And the idea behind that is the more species you get, the easier it gets. So we've done the difficult part now, but with more and more species, it's going to be very simple to annotate microRNA genes in the future. And then that's what I just said. We use more species to increase confidence, and all fish microRNA sequence have a TELEOST last common ancestor ortholog that we define, and based on that we can propose an automatic annotation. And in that case, for instance, that's what we had for this microRNA, and we came up with this annotation because it was the one found in the closest related species here and here, stickleback and medaka. Okay, so what we have identified 660 unique mature mRNAs expressed in our data set, and they correspond to 666 genes. It's not expected that it should be the same number. It's totally unexpected, actually. It's just by chance, right? And you have to understand that if you work with the salmonids, that sometimes the orthologs are very similar. The homologs after duplication. So, and because it's a short sequence, 2 homolog genes can give exactly the same mature microRNA, right? The sequence is the same, and you don't know from which homolog it's coming. Anyway, so don't look too much on this number. It shouldn't be the same, but it's the same. And when it comes to genes, we have 42 singletons. We have 282 genes in duplicates. And we have 26 miR430 genes, which always we deal with separately because they are complicated. They're in clusters. So that's a big leap in comparison to the previously described 354 mature microRNA in rainbow trout in 21 from 280 genes. So we've made a big increase in our knowledge. And please note that we have an 87 retention rate after whole genome duplication based on those numbers. Okay, and that's actually what I'm also interested in. And so we have 87 in this study based on 322 pre-whole genome duplication genes. And in the rainbow trout genome paper in 2014, I think, quite a while ago, we came up with a 97% of retention. but it was done only on 241 pre-duplication genes, and they were located on highly conserved synthetic regions. Okay, so I mean it's consistent, but it's probably a little bit lower than what we had calculated before. So you can see an example of duplicated region in rainbow Chuan, and you see that the microRNA genes in red are almost always present in duplicates. Okay, so we did the same thing. So rainbow Chuan was more difficult because of the duplication. We have to work from one TGD species and try to map on the two homologs. But for CBRIM, it was much easier, and we ended up with okay. So you see the same type of information. So the number of microRNA contributed from the different species. You can see that, for instance, stickleback, medacar are providing high number, and you can see that here, again, the vast majority of microRNA are supported by at least two species. Okay. And we end up with 333 genes, including 20 miR430, and that corresponds to 479 unique mature microRNAs. And actually, 88% of the genes have both strands annotated, so it's actually very good. We are very happy with the CBAS annotation. Okay, so maybe that was a little bit too short, but we'll have some more questions. But in summary, we've provided a comprehensive microRNA annotation. Well, we succeeded in both rainbow Chuan and CBRIM. It took us some time to develop this, automatic annotation pipeline, but it really helped both in terms of speed of the process. At the end, it's super fast to do it. You run it, and then, one day of work, pretty much you have I would say, decent annotation. And also, in terms of accuracy, of course, when it's automatic, you lower the chance of making mistakes. And actually, most of the problems that we had is that we run the pipeline and we found some inconsistencies, and then we will look back, and actually they came from mistakes that we'd done before when we manually annotated the species. So I think now it's going to be, we are on solid ground, and it's going to be much easier for other species. So, and I mean, when you see that, you clearly know why, but the higher number of species you get, the easier it gets. So, and that makes sense. So, what's next? We will annotate. We will use this annotation and expression data to implement the fish microRNA database. Well, mostly the body maps actually, and we will also annotate the other AQUA FAANG species the same way. Probably carp is going to be more difficult, but for the regular TGD species, should be pretty straightforward. And that's it. Thank you.